does it? Levi, did yours work? Did it abort at all?
What is it?
Did it abort at all?
No, I haven't tried to run anything. I've opened a new R markdown.
Yeah.
As far as like the extent of it.
So our markdown was still working. Yeah, so I'm not finding that. I don't see it. I don't see where that project is coming up. So I can email it to him. So go ahead and open up one of your projects.
It is telling me an error message at the bottom.
What's the error message?
Saying package is wide and no small before 21.
We'll see if it actually updates it. Go ahead and open up RStudio. All right, so do you have a markdown package?
I don't know if I have those things. They don't say.
Okay.
Try to find that one.
All right, I think we are streaming. Okay, let me let's open up R.
Yeah, I have an old one.
Okay. If you've got an old one, open it up and see if it'll work. So that's one of the issues. Yeah, go ahead and open it up and see if it'll work. I'm gonna go ahead and session all chunks low. Raspberry. Oh, how come raspberry?
It's not showing me an error, but it's not like it's supposed to.
Okay. Oh, yeah, so this is a change. So what we're gonna have to do is strings as factors.
Okay,
Okay,
thank you.
so we'll keep going and see how that works. All right, so I don't even know if anyone's on here. We started, but yeah, we've got some playbacks. All right, so still had a couple errors in our markdown working in the computer lab. I think there's 2 computers left that still need some fixes. One thing that we just did twice is update the packages. So some of the packages weren't updated. So what you can do is just go to your packages and hit update, and it'll pop up if there's packages that need to be updated, and then go ahead and run that. So hopefully things work. Things are working better, hopefully. All right. So we've got exam today. I'll be available during lab time. I'll come down here, see if anyone's in the computer lab. If not, then I'll probably just hang out in my office working on presentations or exams or something like that. So 2 parts to the exam. The quiz part, that's just multiple choice, multiple answer type questions. It's a mix. Some of them would be like, what are the assumptions, and you can pick multiple ones. Others are choose the test, and I think I set it up just as a multiple choice. That way you don't go ahead and clicking multiple tests to run. And then part 2 is the R markdown. Remember with the R markdown, and I think I set it. I set it on the introduction or the instruction part that if you get a nit error on line 3, check your quotation marks around the date, because it's if we have double quotation marks, then it'll be single quotation marks on the inside. If it's single quotation marks on the outside, it's double on the inside. So I can help you on those. All right. And let's move on. So we had assumptions. All assumptions are met. That has been what we've been working through for the introduction to the ANOVA, how to set up the ANOVA, how to look at the ANOVA table, and then post hoc tests. All right. What happens when our assumptions are violated? So it kind of goes back to that first question of why even worry about it? We worry about it because we're using a test statistic F. We calculate an F, and if our assumptions are met, then we use the F distribution to get our p-value. All right, so if all of our assumptions are met, then our F statistic follows that F distribution. If we violate our assumptions, then we won't follow that distribution. So here's an example. So I made a data set, made sure all our assumptions were met, and then what I did was generate a random number of F statistics, observed F statistics. So I did a permutational ANOVA, which we'll do. I'll show you how to do that. And out of like 10,000 of my replicates, this is the histogram of all of our F statistics. Now, if our assumptions are met, then our F statistics follow the F distribution based on the degrees of freedom, numerator and denominators, and so forth. So you can see that the blue line and the histogram match up fairly well. There is variation. But what we can also do is do one of these QQ plots to show you that, yeah, our F statistics for this permutational ANOVA followed the actual F distribution. And it did that because our assumptions were met. But if we violated our assumptions, then our F statistic no longer follows that F distribution. Now, the histogram and the line overlay looks to be a little bit close, but note our line here. All of those points fall outside of our confidence envelope. We no longer follow our F distribution. So if we don't follow our F distribution, then our p-values are going to be off. Our p-values are going to be incorrect. All right? So what do we do if our assumptions are violated? It ultimately comes down to what assumption was violated. All right? So if we violate our homoscedasticity, so we're normally distributed, but we have unequal variances, then what we're going to run is a Welch's ANOVA. All right, this Welch's ANOVA is going to adjust the F and the degrees of freedom to account for the unequal variances. Now, this test is more powerful and less likely to commit a type 1 error as the data become more and more heteroscedastic. All right, so that kind of leads to the question, well, could we always do a Welch's ANOVA? And yeah, you can. That's that the T-dot test where it said var dot equals T or equals F. The default is that they're not equal. So they're doing a Welch's t-test. And more people are doing those Welch's t-tests and the Welch's ANOVA because there's, if our assumptions are met, it's just as good. It's just as good. And if there's any doubt that we have unequal variances, Welch's is going to be a little bit better. Now, how do we run it? We run it using one-way dot test. So unfortunately, it didn't have an option to pass a linear model. So what we have to do is use the one-way dot test function in order to operate. And as I think about that, let me check my one-way dot test. Make sure that we're not surprised by it. Yep, nope, still needs a formula. Still needs a formula. So we would give it the same formula as we've used for a t dot test, all right, and we'd use var dot equals f. So if you can guess, if I did var dot equals t, then we just run a regular ANOVA, and we'll get the exact same numbers that we would get if we made our linear model and so forth. So you could ask, why on earth did I create the linear model and use ANOVA to get our tables and so forth? The graduate students will see why. All right, this is basically only with two variables, a continuous dependent variable and a categorical independent variable. As soon as we start becoming more complex, this won't work. All right, so if we run a Welch's ANOVA and we get a significant p-value, meaning at least one mean is different, then we need to run a post hoc test. All right, we can't run a Tukey's because Tukey's assumes that it has the same assumptions as an ANOVA, and we violated that assumption. So what we're going to have to do is use pairwise Welch's t-tests as a post hoc. So we're actually going to do our t-test, save our p-values, and then manually adjust our p-values to account for that inflated type 1 error. What happens if we violate normality? If we violate normality, we've got some options. All right? So one thing we can do is just go ahead and proceed with the ANOVA. So we're non-normal, but Fligner-Colleen suggests that we have equal variances. So one thing we can do is just go ahead and proceed with ANOVA as usual. Why? Because ANOVA is robust against slight to moderate to slight violations of normality assumption. All right, it's going to do a good job. So if, let's say we have 5 groups and 3 of them look like they're slightly non-normal and 2 of them look okay, go ahead and proceed with ANOVA. I think we're, some of might not be normal. That's okay. ANOVA is robust. The downside, though, is if we do that, we have to recognize that Tukey is not as robust to that violation. So we can run an ANOVA, but then our post hoc test, we're going to have to do some alternatives to deal with that non-normality. All right. Now, if we have a large sample size per group, so large sample sizes within each group, it becomes less of a concern to fix it. And what we'll probably do is pairwise t-tests if we have low counts. But again, with the pairwise t-tests, we still have to account for that non-normality. And I'll show you how we can kind of address it. If it's unacceptable, if we look at it and say, yeah, this is clearly non-normal, I don't want to take the chance, then we can do one of these other 2 tests. So a Kruskal-Wallis test is a non-parametric version of ANOVA. It's going to use medians, though. So instead of comparing means, we're going to compare medians. And it's basically the median version of an analysis of variance. It doesn't make that normality assumption. But it does make that equal variance assumption. So it kind of does require that part of it. And that test is okay. It's pretty easy to run. It's Kruskal.test. The function's built in. We give it a formula, all right, and we'll be comfortable writing these formula. I would probably run this if we were highly skewed, and I knew that we had our variances that were basically equal. It gets across a central tendency very well. Yeah, it's not the means, but with highly skewed data, you're probably going to be comparing medians because the medians are more representative of that central tendencies. But just like our Welch's, if we're going to run a Kruskal-Wallis test, then we can't run a Tukey's. Tukey's compares the means. We're comparing the medians. So what we'll have to do is then a series of pairwise Kruskal-Wallis tests in order to figure out which medians are actually different from the rest. Our last option is a permutational ANOVA. So what we would do is do a randomization test. Basically, shuffle our groups. So we collected our data. Each of our measurements belong to a specific group. What we're going to do is take that collection of groups and redistribute the labels. And repeat this over and over and over again. And that represents our null distribution. So under the assumption that there is no group effect. All right, and then we compare our test statistic to that null distribution. All right, the p-value represents the number of those randomized f values that equal or exceed our observed. And if we get a small difference, if we get a small p-value, then we know that the group is significant. There is a difference in our means. If we run this, and this test isn't terribly difficult to run, we'll get the script. But if we choose the permutational ANOVA, then we really can't do any sort of two-piece post hoc test on it. We're going to have to continue doing permutational ANOVAs as our post hoc test. And we can do permutational t-tests as well, or since you have the code for the permutational ANOVAs, just run permutational ANOVAs as our post hoc test. But like our pairwise t-test or pairwise Welches that we talked about, we're going to have to adjust our p-values. We have to account for that inflated type 1 error. All right. Now, what happens when we violate both normality and equal variance? Permutational ANOVA. That's all that we're going to be able to do, and our post hocs are going to be the same. All pairwise t-tests. So I do note that we could run a permutational ANOVA just across the board, regardless if we violated our assumptions or not. But my recommendation is that if our assumptions of ANOVA are met, just run ANOVA. People know what it is. People are familiar with saying ANOVA, and most people know how to run one. They've recognized two-keys before. Everything makes sense. If you run a permutational ANOVA, you have to explain, in some cases, extensively what you're doing and why. For some reason, you say, I'm going to run a permutational ANOVA because we violated our assumptions, and people will come back and say, well, you can't just do that. You've got assumptions to meet. It's like, no. By running our permutation test, we've kind of eliminated most of those assumptions. Not all, but we've eliminated the normality assumption and the equal variance assumption. Likewise, if we violated only the homoscedasticity assumption, the equal variances, it's so easy to run Welch's, and again, it's a common test that I'd suggest just do Welch's ANOVA, be done with it, get your p-value, and move on. All right, so we're going to go through data sets that violate assumptions. All right. The first one is Oaks, oaks.csv. So this represents diameter oak trees at 4 locations around campus. We're going to ask the question, are the trees similarly sized? We're going to assume that our data set represents a random and independent sample. Could be, might not be. All right, definitely if we were trying to compare trees, oak trees to other parts of Tom Green County, we violated it because we've collected only on campus. But since we're on campus, we'll assume that we randomly picked oak trees out and measured their diameter. All right, so in our data set, it's posted, so go ahead, download it, and get it into R. And R marked. Opened. Move this over. Ooh. I guess I can't. Move this over here. So on the new versions of R, when you open up the file, I'm going to call it Oaks. I'm going to actually make it lowercase. got my heading, that's marked. I'm also going to do the strings as factors. That was, I want to say it was a default option. I never really had to put it in, but now it seems like we do have to do that. So this site is letters. It's going to read that as a string. All right, we want R to recognize that those strings actually represent factors, so when we use our plot command, it's not going to complain that xlim is or that we need finite xlim or something like that. So when I import it, you'll see the code, and it's going to mark strings as factors equals true. So if you open up any of your older markdown documents and R complained about having an xlim that's finite, go back to how you imported it and make sure you set strings as factors equals true. So make sure you set that. All right, so I've got my data sets in here. This. So if we look at our data set, I'm just going to do it here. All right, we've got two variables. We've got site, that's our categorical, that's our independent variable, and then we have diameter, that is our dependent variable, and its measurement, it's a continuous variable. All right, so our question is, did diameter vary across the sites, or did site have an effect on our diameters? All right, so we've got either or question. Both of them, both questions that I've proposed, wants to use an ANOVA. All right, so what we want to do is check our assumptions first. Okay. So our assumptions, are they random and independent? Yeah, I'm going to tell you, yes, they are. We've collected data to ensure that it was. And then we've got these two other assumptions. So first thing we do is you check normality, see if the data are normal. Based on that, then that normality assumption dictates whether we run a Brown-Forsyth or a Fligner-Colleen test. And in preparation for all this, I'm going to get a library section. Get car loaded. So go ahead and check your assumptions. See which assumption was violated. Check assumptions. Good review for the exam today. Good review for the exam today, right? Checking our assumptions. Uh-oh. Error.
I think that was just on my end.
Did you load car? I know what you did. Check which one's your independent variable, which one's your dependent variable. Which assumption was violated?
Well, I am hung up on that one word, so not a good question for me.
What do we use to check our assumptions? How come I don't have? I don't. Oops.
The assumptions of what normality at each site. Use QQ plots for that, right?
Yep.
Yeah.
How come my environment doesn't show up? That's crazy. Oaks should be available. It is. Huh. Might have to recreate it. So here, let's save this as. Let's see, we'll go to live. Figures. Oh, that's it. Still don't know why that global environment doesn't work. Huh. All right, well, QQ plots. Diameter as a function of site. Oops, air and QQ plots. Air and QQ plot. So we have that one looks slightly curved, but all of our points are inside the confidence interval, so I'm going to be okay with that. I think all the other ones, all the other sites, they look pretty good. They look pretty good. So it looks like we're normal. Interpretation. So we look normally distributed within each group. So now we're going to do Brown-Forsyth. Mean test, we're going to do diameter as a function of site. Data is Oaks. And I get a significant p-value, pretty significant. So we are definitely, what I would say is, have unequal variances. And I didn't do this, but if we did our plot, and look at it, you know, one of the things we look at is if we run our test, does it ever look like, should we expect a significant p-value or not? So just looking at here, yeah, I've got my medians here. I've got this median isn't captured by these two. These, maybe the interquartile ranges overlap a little bit. Maybe they don't. I don't know. It's kind of tough to say. Maybe just slightly. Not going to be surprised to get a difference. But important thing is look at the difference in our interquartile ranges. You got a big one, you got a narrow one. Look at the whiskers. All right, we've got variation in the magnitude of those. That right there is suggesting that I might have some unequal variances, and we needed that assumption because R is comparing our variances. All right, R is using the variances to figure out that signal to noise ratio. Do we have more signal, more variation from our groups to our grand mean? Is that more than just the variation within each of our data sets? So right now, we've got a lot of variation, and that's going to cloud up any of our signal that we have. So just looking at this, I'm not surprised that we have unequal variances. So that means then that we can't run our ANOVA. And I mean, there's no doubts about it. We can't run it because ANOVA requires it. And it would be a pretty big mistake to run. All right, so with the Oaks data set, we'll run a Welch's ANOVA. All right, that function is one-way.test. So one-way.test Welch's ANOVA using the function one-way.test, and we're going to write our formula. we're going to write our formula. All right, so y is a function of x, our dependent variable, as a function of our continuous variable, and make sure we have var dot equal equals false. So, one-way dot test, we have diameter as a function of site, data is oaks, var dot equal equals false. And when I run it, we'll get our output that tells us everything that we need to know. So we ran a one-way analysis of means. That's basically your ANOVA, but we're not assuming equal variances, and that's our Welch's part. Right? That's our Welch's part. Now what I want you to see is check out our degrees of freedom. So we've got our F statistic and then the degrees of freedom. Our degrees of freedom have always been whole numbers. And now we actually have a decimal. All right? And that's what Welch's is doing. Welch's is trying to correct for that unequal variances by adjusting the degrees of freedom. And it's the same thing with the Welch's t-test. We're going to, more than likely, you're going to get a degrees of freedom that has a decimal. All right? And we report that. We have to report that decimal. All right? So we've got our F statistic. We have degrees of freedom 3, degrees of freedom 119.76, and that gives us the p-value. So what's our conclusion and what's our write-up? So our conclusion, our mean diameter of oaks varies by site. And then the test that we ran was Welch's ANOVA. All right, so we're going to do our F statistics. So our F is 3, 119.76. That's our degrees of freedom. Our F statistic is 31.74. And our p-value is less than 0.0001. All right, so we did our interpretation. All right, so one-way dot test, that's what we got. Here's our write-up. Just remember, the null hypothesis of Welch's ANOVA is the same null hypothesis as the regular ANOVA. All right, our means are equal, or the alternate is that at least one mean differs from the rest. All right, so data are heteroscedastic. Welch's ANOVA told us that there is a difference of means. At least one mean is different. So what now? What do we do? Well, we can't perform Tukey's redundance because both of those required equal variances. So what we're going to do is run a series of pairwise tests with a p-value adjustment. All right, so these pairwise tests are going to be 2 sample tests. We're going to compare site A to site B, and then site A to site C, and so forth. We're going to run all pairwise combinations. We're going to collect our p-values. And then, once we get our p-values, we're going to adjust them. Why? It's because every single test we have has an alpha level set at 0.05. Right? Every time we run a test on the same data set, we're going to have an alpha 0.05. So each of our pairwise tests has an alpha 0.05, but the collection that tells us which means are actually different from the rest is going to start to increase with each test that we run. So what we want is a family-wise, an alpha family-wise of 0.05. So the family-wise is the collection of tests, and we're trying to get back to 0.05. So how do we do that? Well, we're going to adjust our p-values to make that happen. How do we adjust our p-values? It's not too hard. There's a p.adjust function built into R, but that takes all of our p-values. So what we're going to do is run a series of tests. And we can run a Welch's t-test, we can run a Welch's ANOVA to get our p-values. Our p-values are going to probably be the exact same, regardless of what we use. But what we're going to do is run our t-dot test, use our formulas, but now we're going to use var dot equal equals f, all right, to run a Welch's t-test. So what we're going to do is run pairwise comparisons. We're going to run A versus B, A versus C, A versus D, B versus C, B versus D, and C versus D. So you can see we're running a total of 6 tests is what we're going to run. Each test has an alpha of 0.05. Our family-wise is going to be greater than that, so our adjustment then will get us back to that alpha of 0.05 level. So what is my recommendation to do this? Well, my recommendation is that we're going to create subsets. We're going to create our subsets and then run our t-test where data equals that subset. Why is that my recommendation? Well, the alternative is to use the subset built into R. So let me open up t.test, or one way, right here. Scroll down a little bit. So this is a one-way.test help file. All right. And you can see one-way.test, we've got our formula that we specified. We have our data down here, and then we have subset. We can actually specify a subset in the code itself, and it would run our test on that subset, which is fine. The same thing applies for a t.test. So if we go to t.test, we have, move this over, we have formula, and then we have the subset option. Now, the reason I suggest making our own subsets and then passing the subsets to our function is that if we ever want to go back and look at the individual subsets, then they're already created, and we save them. And also with our subsets, it helps us keep track of what comparisons we're doing at any one time. So our subset function, remember, is this. Now, we lucked out. You lucked out. Yes, we all did now. We all lucked out because the QQ plots, the updated car package, allows us to write a formula, and then it makes all the QQ plots for us. It doesn't do that for all of our pairwise tests. All right. So what we're going to do is create our subsets using this function. So subset, our data, and then we've got 2 selection variables now. We're going to pick out our grouping variable where we have site A, and then we have our grouping variable with site B. And what we use is this pipe symbol to specify the OR component. So we're going to take our data, we're going to create a new data frame where we specify variable equals condition 1 or our variable is condition 2. So here's the start of our subsets. All right. So what I'm going to do is just this: levels of our Oaks $ site. First up, I need to know what my options are going to be, what levels I have in the data set, because I have to specify it exactly. I have to specify that level exactly. So I have A, B, C, and D, and the quotes told me that they're strings. All right, so since they're strings, I'm going to be using quotation marks. So then what we're going to do is every pairwise comparison. So I'm going to do A to B. So I'll do AB dat, what we'll do is Oaks AB. So Oaks data set only cites AB. We're going to do our subset. And we're subsetting our Oaks data set where cite double equal size A, pipe symbol, cite double equal sign B. All right, so we're taking a subset of our Oaks data set where our site is equal to A or our site is equal to B. And when I do that, I'm going to get a data set of only A and B. So just to kind of demonstrate it, I'm going to show the one side of it. So I've got B's and A's, and if I just kind of cycle through these next pages, you will see that it is only B's and A's in our data sets. All right, so we took our subset, and now our data set is oaks.ab. So then when I do my t-test or a one-way.test on it, I reference this data frame, and the only levels that are there are A and B. I can now just run a 2-sample test. So I check to make sure this works, and now I'm just going to copy and paste. 1, 2, 3, 4, 5. All right. Now I obviously don't need all 5, but what we're going to do is we did A and B, A and C, A and D, and then we do B and C, B and D, and then C and D. So I did all my combinations there. And now I have to update this. So this one's A and C, that one's A and D, this is B and C, and this one's B and D, and then this one is C, and that one's D. So I made sure it worked one time, that I got what I wanted, then I copied and pasted it and updated all of my references. So now, when I run this, I will get 6 data sets. And why it doesn't appear in my global environments, I have no idea. I have no idea. Hopefully yours does. Does yours?
I don't know.
It's on this computer. It must be on my account. So now, we're going to run pairwise tests on each of the data sets, on each of the subsetted data sets. So I said t.test. T.test, we are doing diameter as a function of site. The data isn't on Oaks. If I try to do data equals Oaks, it's going to fail. It's going to say you've got basically more than 2 levels, or it says it only requires 2 levels. But what I'm doing is Oaks.ab, and then var.equals, var.equals f. var.equals f. So then when I run it, you can see that it works, and it only compares group A versus group B. So that's our first comparison. Now, that p-value is the p-value of the test. That assumes an alpha of 0.05. But we don't want that. Okay? Because all 6 tests, each of them has an alpha of 0.05. We're going to increase our chance of making a type 1 error. So what we're going to have to do is save this p-value. We're going to save this p-value so that we can adjust it. All right, so saving the p-values for later adjustment, I like to make a vector called p.val, and then I am writing my p-values as I get them. And then what we'll do on Wednesday is talk about the adjustments, how to do this, and the resulting p-values that we report. Now, looking ahead, when we report the results of this test, because we're running these pairwise tests, we do have a test statistic, we do have degrees of freedom, all right, and we have a p-value. But the only thing that we're going to report on these post hoc tests are these adjusted p-values. Not the ones that are there, these adjusted ones that get us back to a family-wise alpha level of 0.05. All right? All right. We'll end it here. Again, I'll be around. I'll be available this afternoon, at least until about 4:30 or so.
Should I wait until after this exam to come see my standing?
Probably. Probably. All right. Email if you have questions.